Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory combinatorics based on my book, An Invitation to Combinatorics. The subject of this lecture is small Ramsey numbers. We will prove that R34 is 9, R35 is 14, and R44 is 18. I will explain what those things are. I have had two other videos on Ramsey numbers. One, what is one Ramsey numbers, and the other one, the proof of Ramsey's theorem for two colors. And I urge you to watch those two videos before watching this, although I will remind you of the necessary definition and notation. If you're not familiar with the notation, that's fine. But if you've never heard of Ramsey numbers, then this is probably not a good place to start. So RMN is going to be a Ramsey number with parameters m and n, and I will explain that in a second what that means. We have previously, in one of the previous videos, shown the well-known fact that R336, all that means is that if you take 6 vertices and draw all the edges between them, that's called a complete graph on 6 vertices, K6. And then if you assign one of two colors, red and blue, to the edges, then you're guaranteed, no matter how you do the coloring, no matter how hard you try, you're guaranteed that you will have a monochromatic triangle. You will either have a red triangle, a triangle where all 3 edges are red, or a blue triangle, all the edges are blue. In here, what we'll want to show is that R34 is 9, and R35 is 14, and R44 is 18. And I want to tell you what it means to say R34 is 9. What that means is that if you take 9 vertices, here 9 vertices, and I've drawn all the edges between them, so this is called the complete graph on n vertices, K9. And then what I do is that I arbitrarily color the edges. In fact, I won't do it. You can do the coloring. You can try any coloring you want, and then I will have a prediction for you. What I'm looking for, this 3 and the 4, the 3 stands for the fact that in the first color here, blue, I'm looking for a triangle, and the 4 stands for that in the second color, I'm looking for a complete graph on 4 vertices. So I'm looking for a K4. So 4 vertices such that all of their edges between them are of the same color, of the second color. In this case, I'm denoting that by red. So I'm looking for either a blue triangle or a red K4, not just the 4 vertices that are connected by the red edges, but 4 vertices such that all their edges are red. And so how am I going to do that? Well, I'll start with a K9. I will color the edges any which way, arbitrarily. In fact, as I said, the best way to think about it is that I'm not coloring it, you're coloring it. And then what I'm telling you, my theorem tells me that in this mishmash, you can find yourself either a blue triangle, or if you can't do that, you can find yourself a red K4. Of course, you can't promise a blue triangle because you could just color everything with red and then there won't be any blue anything. But that's where the or comes in. I have a blue triangle, or if I can't have that, I will have a red K4 for sure. We write this fact as the notation we use is that K9 arrows to K3 comma K4. So again, all that means is that color the edges of K9 with one of two colors arbitrarily, and then you're guaranteed a blue K3 or a red K4. Of course, the two colors should be blue and red. To say what the Ramsey number is 9 is to say that 9 is the smallest such number. In other words, it's to say that K8 doesn't arrow into K3 or K4. It's possible to start with a K8 and color the edges in some way so that there's no blue triangle and no red K4. And we will show that later in this talk. So that's what we want to prove. We want to prove that why is it that if you start with a K9 and start coloring the edges, no matter how you do it, why is it that you're guaranteed a blue K3 or a red K4? And through an example, why is it that K8 does not provide the same conclusion? So now I'm going to remind you of the stuff that I just said one more time, just to make sure that we are on the same page as far as the notation is concerned. KS is the complete graph of order S. That means S vertices, and you draw all the edges between them. Now, then what we do is color the edges of KS, blue or red, arbitrarily, and we are asking, can you guarantee a blue KN or a red KM? Now, S is just a number. S could be 47. So you're taking 47 vertices, drawing all the edges between them. N and M are two integers. So N could be 35 and M could be 5. And I'm asking, if you take any K47, color the edges with blue and red, are you guaranteed a blue K35 or a red K5? And the answer, most likely, if you just make up those numbers, is going to be no. Sometimes the answer is yes, but not often. So when it is, we write it as ks arrows to kn comma km. The way we want to think about it is that this is a claim. Someone is saying that ks arrows to kn comma km, meaning that, again, if you color the edges of ks blue or red arbitrarily, you are guaranteed a blue kn or a red km. This claim could be true or false. And again, the claim is that arbitrarily color the edges of a ks using two colors, blue and red, and then you're guaranteed a blue kn or a red km or both. You have to decide which one is the first color and which one is the second color and what your wish list is right at the beginning. You can't change midway through the stream and then say that, oh, look, I couldn't find a blue kn, but I can find a blue km. No, that doesn't count. Blue kn or a red km. Ramsey's theorem, again, subject of a previous video, was that if you pick any integers n and m, positive integers, that's going to be your wish list, then there exists a positive integer s that will depend on n and m, most likely much larger than them, such that if you start with ks, then it does arrow to kn comma km. If you start with ks and do the coloring, you are assured a blue kn or a red km. Again, order out of chaos. You start with ks and color it every which you want, but unbeknownst to you, there is lurking in the background a blue kn or a red km, no matter how you do the coloring. This is an amazing theorem, and the proof of that is in a previous video. So what's a Ramsey number? Ramsey's theorem says there is some integer that ks arrows to kn comma km, but if it works for an integer, it also works for bigger ones. So if you get it to a complex enough system that you're assured a blue kn or a red km, if you make the system larger, or of course you will also have that, but the smallest one, that's such that ks arrows to kn comma km is denoted by r and m, and r for Ramsey, and this is a Ramsey number. So some very quick facts about it. Well, if you switch the name of the colors, well, of course it doesn't matter. So RMN is the same as RNM. R1M, what does that mean? That means you're coloring the edges of some unknown yet complete graph, and you're looking for a blue K1 or a red KM. Well, what's a blue K1? It's just one vertex with no edges, and you have that no matter how big your KS is. And so for that, the S needs to just be one. As long as you have one vertex, you're assured this. What about R2M? You're looking here for a blue K2. That's just a blue edge. And for that, you just need M vertices, because if you have M vertices and draw all the edges and color them, either you will use blue or you won't. As soon as you use blue, you have a blue K2. If you don't, well, the whole thing is a red KM. Previously, we proved that R33 is 6. Again, that was actually a very cute argument. If you haven't seen that, I urge you to watch the first video. We also showed, this was actually how we showed Ramsey's theorem, is to show that RNM is less than or equal to RNM minus 1M plus RNM minus 1. So this is sort of a recursive upper bound. And so this proved to us that RNM exists because of these initial conditions, because we already knew that R1M and RM1 are 1. Then we knew that when you go higher up, you can use these and generate bounds. Not necessarily find RNM, but you can find a bound. And if a bound exists, then you know that, well, there's some S work, so there must be in the smallest one. Actually, using that and using some of these things that I said, we can actually show that R33 is 6, or at least is less than or equal to 6. So R33, according to that recursive rule, is less than or equal to R23 plus R32, and R23 and R32 both are 3, so R33 is less than or equal to 6. To show that it is 6, you have to show that it's greater than 5, and all you have to do is draw 5 vertices and draw all the edges around red and all the edges inside blue, all the other edges blue, and you will see that you won't have any monochromatic triangles. From this, what happens for R34? Well, you get that R34 is less than or equal to R24 plus R33. R24 is 4, R33 we just showed is 6, so we get it's less than or equal to 10. The fact is that R34 actually is 9, and that's the purpose of this lecture, is to bring that 10 down to 1. And you might think that 1 is not that much, but that actually takes a little bit of work. Here's our strategy for proof. How am I going to show that R34 is less than or equal to 9, and then later R35 is less than or equal to 14, and R44 is less than or equal to 18? Well, I said that we proved this recursive relation we are going to, in a specific case, improve on this. Not improve on it a lot, but just a little bit. So this is an upper bound. It says RNM is less than or equal. Here's this bound. RNM can't go above it. To make it a better bound, we need to bring that bound down. If we bring it down, then we have made a stronger statement. Then we were limiting RNM to not go up even less than before. And this is what we're going to prove, that if n and m are integers greater than 1, and if it happens to be that Rnm minus 1m and Rnm minus 1 are both even integers, they're like 0, 5, well, not 0, but 6, not 5, not 0 or 5, 6, 4, 12, 18, even numbers. If they're even integers, then Rnm is less than or equal to Rnm minus 1m plus Rn comma m minus 1 as before, minus 1. So it's 1 less, and that will be enough for our purposes. So then we'll say, for example, that R24 and R33, R24 is 4, R33 6, both even 4 and 6, and therefore R34 is, we can now prove, if we prove this theorem, the blue theorem here, that it's less than or equal to 4 plus 6 minus 1, which is 9. And then we will come up with an example to show that it can't be any smaller. And also, what about R44? Well, R44 is less than or equal to R34 plus R43. R34, we just showed that it's less than or equal to 9. That's not even. That's why we can't use this new theorem. We have to go back to the old one. But because now we have a better bound for R34, we will be able to show that that's less than or equal to 18. Just from this, we will know less than or equal to 18 and not equal to 18, and we will need an example to show that it is an 18. And the same with R35. R35, according to our old rule, is less than or equal to R25 plus R34. R25 is 5, and R34, again, we will show that it's 9, and so this will show that R35 is less than or equal to 14. So this one little blue theorem here, showing that if both of these things are even, then Rnm is not just less than or equal to Rnm minus 1 comma m plus Rn comma m minus 1, but that thing minus 1, it's a little bit smaller than that, is enough to get us all these Ramsey numbers. And then, bootstrapping, these will give us better bounds for the higher ones. They won't give us exact ones for the higher ones, but they will give us better bounds for the higher ones. Okay, so now how is the proof is going to go? So we know that these two numbers are even, and we want to show that Rnm is less than or equal to that sum minus 1. So what we're going to do is that we're going to let S be that humongous number. And what we're trying to show is that if you have that size system, then you will then it will work, and you will get a blue Kn or Km. In other words, we want to show that Ks, what's S? S this Rn minus 1 comma m plus Rn comma m minus 1 arrows to a blue Kn or a red Km. That's what we want to show. So I want to convince you the proof of the pudding is in the eating. I will start with a Ks. I will color the edges with blue and red arbitrarily any way you like. And I want to show you that there's a blue Kn or a red Km. That's my strategy. How am I going to do that? Well, I will say, look at one of the vertices of this Ks. What's the degree of that vertex? How many other vertices is it adjacent to? Well, the degree is S minus 1. S minus 1, what is that? Well, what is S? S is that sum minus 1. So S minus 1 is that sum minus 2. So that's how many edges come out of V. Now, I'm going to make a claim, and I will argue why that's true. I will say there are 3 cases. It might be that there's at least Rn minus 1 m blue edges that incident with V, that come out of V. Well, sure, there could be. I mean, this many or more. Or it could be that there are this many Rn m minus 1 red edges incident with V. That could be. Now, what happens if neither one of those are true? If neither one of those are true, then I claim that there's going to be exactly Rn minus 1 m minus 1 blue edges, and at the same time, exactly Rn comma m minus 1 red edges incident with V. Why is that? Well, just think about the third case. Maybe that's true. Well, if that's true, that's good. If not, then if this is not exactly this many blue edges, then it's either fewer or more. If there's more, well, then that means that we are in case 1. Well, and if it's less, then then that means that there got to be more red edges because they have to add up. The number of blue and red edges have to add up to the degree of V. If there's fewer blue edges, then there must be more red edges because these two numbers add up to the degree. So if you have fewer of one, you've got to have more of the other one, and then you end up in case 2. So either you have exactly this many blue edges and exactly this many red edges, or if you don't, then one of them will be more, one of them will be less, one of them will be more. Well, the other one will have to be more, and then we will be either in case 1 or case 2. Okay, so now let's go do it. Case 1 and case 2 are actually ones we have done before. They're the ones that we proved in the original bound. It was the same argument, but I'm going to repeat it quickly. So let's say that we have r n minus 1 comma m blue edges coming out of V. So then what do I do? So what is the situation? Edges of KS are colored blue and red, and I'm looking for a blue KN and red K or a red KM. T I'm going to let to be this number Rn minus 1m. And we are in the case where we know that T of the edges incident with V means the edges that have V as one of their ends, are blue. This many or more, but at least T of them. So look at the other end of these vertices. Again, this is the same argument that we've had in the previous videos. Look at the T vertices at the end of these blue edges. Those T vertices are all connected together, and all those edges are colored either blue and red. And we know that KT arrows to Kn minus 1 comma Km. How do I know that? Bill, because T is a Ramsey number. T is the Ramsey number with parameters n minus 1 and m. So as soon as I have a KT, and now I do, the other end of those those edges are T vertices all connected together. So that's a KT, and all the edges are colored with blue and red. So because the T is a Ramsey number, is the Ramsey number n minus 1 comma m, I must have a blue Kn minus 1, or if I don't have that, I will have a red Km. Now, so among the T vertices, so that's, I'm saying that again, I have a blue Kn minus 1 or a red Km. If I have a red Km, well, then I was looking for a red Km. I just found it. I'm good. What if I had a blue Kn minus 1? Well, if I had a blue Kn minus 1, then I'm short the vertex. But now I have V, and I know that V is connected to all the T vertices, including those n minus 1 among them that form the Kn minus 1 with a blue edge. And so together with V, those that Kn minus 1 together with V will be a Kn with all edges blue. And I'm going to be good. So that's one case. Case 2 is going to be identical, except the place of red and blue are going to be switched, and we'll make the same argument. Okay, so the remaining, really, the content is case 3. So that's the case where I know that exactly Rn minus 1 comma m minus 1 blue edges and Rn comma m minus 1 red edges are incident with V. In the original theorem, the bound we proved, this case did not come up because this is not enough edges as far as the degree of V was concerned in that case. In this case, because we have made S1 less, this is enough. They add up to the degree of S, so this could happen. Now, the point is, the insight is to say that, well, how did we pick V? V was picked arbitrarily. V was one of the vertices. I didn't say, pick this one because it's better than that one. We just picked one vertex. So we could do this with any vertex. If any of the vertices gave us case 1 or case 2, we would be done. So not only we are in case 3, we must be in case 3 for every vertex. So every vertex must have this many blue edges and this many red edges, not just V. Okay, so S is, again, this number. I'm reminding you, we've colored the edges blue or red. We want a blue Kn and red Kn. And now we know that something about the only case left, that every vertex of this KS is incident with exactly Rn minus 1 m minus 1 blue edges and Rn comma m minus 1 red edges. So Ramsey number minus 1 and Ramsey number minus 1 red edges. Okay, so what? Now we have it really restricted what's going to happen in this configuration. how are we going to get ourselves out of that and find ourselves the right things? And the point here is that let's just count, is to just take a moment and say, is that even impossible? Is that even possible to have every vertex to be incident with this this many edges, exactly the same? And remember something, that we have not yet used the hypothesis that both of these numbers are even. That's an important thing. It doesn't work without it, but we haven't used it anything up to now. So that's going to be the crucial thing. We have to use that. And the question we're going to ask is that how many blue edges in total? That's what we're going to ask. What's the total number of edges of blue edges? Well, we go around every vertex and ask how many blue edges you have, and we know the answer. Exactly Rn minus 1 m minus 1. And how many vertices are there? There are S vertices, and each one of them tells us Rn minus 1 comma m minus 1. So this is the sum total of their answers, but every edge has two ends, and so we've asked this guy, this end, and at that end, how many blue edges you have. So we counted that blue edge twice, and so therefore we have to divide by 2. Okay, so that's the number of blue edges. But note that this Rn minus 1m, it was an even number. When you subtract 1, you get an odd number. What about S? S is the sum of two even numbers minus 1. If you add two even numbers, you get an even number. When you subtract 1, you get an odd number. Both of these two numbers are odd, and yet we're dividing by 2. And so we're not getting an integer. And the number of blue edges must be an integer. So this is not possible. So case 3 is not possible. So case 1 or case 2 are the things that are going to happen. But again, here we use heavily the fact that these numbers were even. In fact, both of them were even. And so case 3 is impossible. Okay, so what we've proved is that if these guys are even, I'm reminding you, then we have this slightly better bound than we had before. And again, then this implies that R34 is less than or equal to 9. It implies that R44, using this new bind for R34, is less than or equal to 18. And R35 is also using that same new bound for R34, is less than or equal to 14. But how do we get equality? Well, we need examples. We need to show that these are the smallest numbers for which our wishes come true, and we get these monochromatic KNs and KMs. And so we need to show that we can't do better. So let's start with R34. We showed that that's less than or equal to 9. We want to show that it's greater than 8. And so what that means is that we have to show that if you start with 8 vertices, a K8, here's a K8, and if you color the edges, not arbitrarily, but in some particular way, then there is a way to color the edges with blue and red so that you do not have a blue triangle and you do not have a red K4. And the proof of the pudding is in the eating. I'm just going to do it. So here's how I'm going to color everything around the outside blue. And I will also color the main diagonals, the diagonals going from a vertex exactly to the opposite one, blue. Note that there's no vertex down there. This is where the diagonals are meeting. The vertices are all around the circle. So so this is my blue edges, and then I'm going to put red edges for everything else. So this is my coloring of K8. And now, if you look at it enough, you will see that if you look at the blue ones, there's no red triangle. There's no 3 of them that all the edges between them are blue. And if you look at the red ones, there are red squares, but there's no red K4. One way to think about that is that to get 2 things here that are connected by red, you have to skip one. And so if you want to do that, if you start, for example, with this one, you have to skip to that one, then skip to that, to skip to that to get the square. But those guys have a blue diagonal, and therefore they're not the whole K4 is not red. And the same with the other red square. And so this coloring shows us that if you have a K8, it's possible not to have a blue K3 or a red K4. However, we proved that with 9, we are guaranteed a blue K3 or a red K4. Therefore, 9 is the threshold. 9 is where the world changes. 9 is the Ramsey number R34. So what about R35 being less than or equal to 14? We proved that, but we want to prove it is 14, so we have to prove that it's greater than 13. And so here's the coloring. So here's 13 vertices, and on the left, I've put in all the blue edges, and on the right, I put all the red edges. I didn't put them together because it would just be too confusing. And you can then try to see, well, you can easily see that there's no blue triangle. You would have to work harder to convince yourself that there's no red K5. In fact, there is a red K4 because 13 is bigger than 9. And so we are guaranteed that among the red, there will be actually plenty K4s that are red, but there will not be a K5. Now, you might think, well, how on earth did someone come up with this coloring? Actually, there's an algebraic way of defining this. If you label the vertices 0 to 12 and think of them mod 13, and then if you look at the difference between any two vertices, like, you know, the vertex 12 and 2, subtract them, you get 12 minus 10 is 10. 12 minus 2 is 10. And that difference, if that difference is a cube mod 13, then you make it blue. Otherwise, you make it red. So there's an algebraic way of generating these that then will help you in proving, for example, that there is no red K5. But in any case, you can stop the video and stare at this long enough to convince you that this shows that R35 is greater than 13. And because we already proved this less than or equal to 14, so it must be 14. And finally, why is R44, well, not why is less than or equal to 18. We proved that, but why is it less than or greater than 17? And again, here's the coloring, the red coloring and the blue coloring that tells us that here's 17 vertices with neither one of them having there's no red K4 and there's no blue K4 as well. And here the coloring has to do with integers mod 17 and square. So if the difference between you label the vertices 0 through 16, and if you look at the difference between two vertices, and if that difference is a square mod 17, then you give it one color. If it's not, you give it a different color and you get this coloring. I'm not explaining that nowhere near enough for you to understand. I'm just making the point that there is actually an algebraic way of sort of generating these. But they're not like obvious. Like, it's not like if you knew algebra, then you immediately would know that would work. It's just that if you say it that way, then proving things about them would be easier. So this video was a third video on Ramsey number. Prior to those, I had a video on basic vocabulary of graphs, vertices, edges, degrees, and so forth. Then there was a video on what is Ramsey theorem. Proof of Ramsey's theorem for two colors was another video. This video is the small Ramsey numbers R34, R35, and R44. Hopefully there will be a video about multicolor Ramsey's theorem, where you have not just two colors, but many colors, graph Ramsey numbers, as well as Ramsey's theorem for hypergraphs. So those will be hopefully future videos. If you like this video, subscribe so that you will get notifications when such videos come up, and like the video. See you next time.